Yeah, so before we actually start the course, we'll try to trigger a few questions and also communicate the most important thing. So at least if you survive the first minute, you should have learned hopefully something that you will never forget throughout your career working with at least PVT and petroleum fluids. And that's essentially the course summary of this particular course, which is that 1 cubic meter is not always equal to 1 cubic meter. And what we mean by that is that it's very, very important that when we talk about volumes in the petroleum domain, that we assign some context of where this volume or what conditions this volume was measured at. So if we talk, for instance, about the reservoir volume of a meter cube, or we talk about a separator barrel, or we're talking about a stock tank barrel, we're talking about very different things. And when I say very different things, there's compositional differences between them, and of course the conditions are different, even though the volumes here is the same. But probably more importantly for the business we're in, the value is also different. So if we just look at this very, very simple example of a reservoir cubic meter is not equal to a separator cubic meter, it's not equal to a stock tank cubic meter. What I mean by that is that the value between these different products, if we think of an oil reservoir, for instance, typically looks something like this, and the value decreases as we go to the left on the slide. And what I mean by that is, you have a reservoir volume that shrinks when it comes to separator conditions, and you also have a shrinkage of the separated oil from separator to stock tank, where stock tank is actually the volume that you sell. So that's very, very important to remember, that volumes, when we talk about volumes, always provide the context of where this volume was measured in terms of pressure and temperature. And you should try to the best, at least that you can, to not just say, when you talk about PVT at least, or PVT sensitive processes, that you just say, yeah, I measured the volume to be 1 cubic meter. You should always be, is it one or one barrel? Is it one reservoir barrel? Is it one separator barrel? Is it one stock tank barrel? Very, very different things. Again, in terms of value, in terms of composition, etc. So that's the first learning of the course. Keep that in mind, bear that in mind as we go through the different topics here. This also has to do with the fact that PVT is process dependent, which is somewhat maybe not intuitive, and we'll touch base on that later. But in reality, actually, based on what surface facilities you have, you can actually change the definition of the reservoir. So you can change the reservoir fluid type based on what you change on surface in terms of facilities, which for many people is a little bit non-intuitive, but hopefully you'll understand the reasoning from that as we move throughout this course. And it all has to do with that PVT is path dependent, which is also another key concept of this course. Very good. Every time when we talk about PVT, one of the first items we touch base on is related to reservoir fluid classification. When we're shown reservoir fluid classification slides, we typically are given a PT diagram, phase envelope, and we'll look at a lot of different PT diagrams in and throughout this course for different purposes. But before we do that, I would just like to try to communicate at least a few different important, I guess, reservoir fluids in terms of just what they produce at surface, and what they produce over, or if it changes over time, what we're producing at surface, and no PT diagrams. So we'll start with the simplest case, which is what we call a dry gas. And if some of these things might happen a little bit quick, or if you haven't been exposed to this before, do not stress, because we'll cover this in much more systematic manner later in the class. But a dry gas reservoir means that you in the reservoir only have a dry gas, so there is no heavier components that translate into stock tank barrels. Essentially, you might have a little bit of water. So here there's essentially a cartoon to the left with some animations, and there's also a pressure temperature graph just to see where we're actually moving in this pressure temperature space as we produce. So if we at the initial production we're producing from this dry gas reservoir, we produce this barrel at surface, and it goes into a surface facility right here. We process the products, and what we produce as an output is surface gas originating from the reservoir gas phase, and we denote that with a G hat G, and we'll touch much more about the nomenclature later. In this particular example, the gas expands about 270 times from reservoir conditions to surface conditions. That's what's called an expansion factor that we'll also talk about later. And if the reservoir, when we produce the reservoir, the pressure in the reservoir goes down, and when the reservoir pressure goes down in a dry gas system, the composition is constant. The composition is the same of the reservoir fluids, and also what you produce at surface is the same in terms of composition. And the reason why it's called a dry gas reservoir is that you're not producing any liquids at surface except from water, of course. Introducing a little bit more complexity is a case where down in the reservoir we're always a gas. That's called a wet gas reservoir. And the only difference from a dry gas reservoir is that when we produce it to surface, we get two surface products, both originating from the reservoir gas phase. So the surface gas, and we also have a surface oil originating from the reservoir gas phase. That's what we call condensate, and we have some condensate production. And with time, when we deplete the reservoir, we still in the reservoir remain single phase gas. So there is no liquids that drops out of solution in the reservoir over time. So if we continue to produce, at late point in time, the surface products that we produce, the compositions of that, and hence the GOR, or the inverse of that, which is called the CGR, condensate gas ratio, is constant through time, and that's the definition of a wet gas reservoir. One of the more complex fluid systems that we deal with in the real world is what we call gas condensate reservoirs. At original reservoir pressure, if the original reservoir pressure is above the saturation pressure, then we're producing in the reservoir a single phase gas. So everything in the reservoir is a single phase before it goes into the surface facilities. And we obtain two surface products, again a surface gas originating from reservoir gas, and a surface condensate originating from the reservoir gas. When the special thing about a gas condensate reservoir is that when we reduce the pressure with time, the pressure can reach what we call the dew point, and at the dew point, liquid bubbles or liquid drops, I guess, is coming out of solution and drops out from the gas, and we actually start to build a oil or a condensate saturation down in the reservoir. This condensate saturation remains typically immobile, so we typically don't produce it from these condensate reservoir just because of gas is much more mobile than oil. And we also get this interesting phenomena related to condensate blockage, which is beyond the scope of this course, but we have another course on Whitson Academy that covers that special engineering topic. Through time, if we continue to produce at pressures below the saturation pressure, since the liquid drops out of solution in the reservoir, and we only produce the gas, there's less liquids in solution with that gas that we produce. So with time, we're actually producing a surface condensate that is less. So the CGR over time, so the producing CGR ratio, typically goes down or goes down with time when we're producing below the dew point. Maybe one of the cases that at least many people on the Norwegian continental shelf are used to is because we have a lot of oil reservoirs there. We also have that many other places in the world as well. Is what is special about producing from a oil reservoir? So if we are above the so-called bubble point, which is the saturation pressure type of a reservoir oil, and we produce a barrel from what's initially single phase, we run it through a surface facility, and we get two surface products again, the surface gas originating from the reservoir oil, and the surface oil originating from the reservoir oil. And the GOR for this particular case is some certain number, and as we deplete the pressure below the bubble point, gas is actually coming out of solution in the reservoir. What's special about this case compared to the condensate case is that this gas is mobile, and you will produce this gas as well together with the oil. And when this gas comes out of solution and you produce it, you actually start to produce from a gas phase that has sometimes it has its own condensate in solution. So in addition, if I just flick back on the screen here we see we're producing a surface gas from reservoir oil and a surface oil from a reservoir oil. But once we get a new phase that started to build saturation that's mobile in the reservoir, we're actually also producing a surface gas from a reservoir gas phase and a surface oil or condensate from the reservoir gas phase. And also that typically means that your producing GOR goes up with time, which is also reflected by the change over here. So that's just a few basics when it comes to explaining the different reservoir fluid types. Hopefully this is a different way that you've maybe seen this explanation before. We'll probably go through a more common way of explaining this later with phase envelopes, but hopefully this have communicated a few key items that make it or that discussion a little bit more intuitive. And actually, before we've learned anything about compositions, about how we measure compositions, petroleum fluids, more on reservoir fluid classification, we'll actually go ahead and do a short quiz. So what I would like you to do is to pause the screen very soon and analyze this compositional measurement right here. This is a molar distribution of a particular reservoir fluid. And just guess whether you think this is a reservoir oil or a reservoir gas. And just for reference, these components in red and I guess yellow is the so-called light and intermediate components that typically make up a gas phase. And this whole thing right here sums up to 1, and we can see that methane is more than just that one molecule, which is a very light molecule, makes up more than 50% of the compositional measurement right here. It's also given that the heavier components, the C7 plus mole fraction, is around 24% or 0.24 in terms of fractions. So take a short break now and do some thinking. Be honest with yourself. What do we think? Great. So now I hope you unpause the video and have a good answer in place. And now I would like you to repeat that exact exercise, but just look at the same. This is the exact same fluid. The only thing is that we've converted the compositional measurement from a mole fraction to a mass fraction. So now we actually don't see, call it the number of components, which is what we are counting here, but the the actual mass amount of each component right here. And you see the huge difference that has for instance, methane, which was if you counted the number of components, maybe 55% of the components, or more than half of it, while when we convert it to mass, it's a little bit shy of 10%. Of the fluid in terms of the mass. While we see the C7 plus mass fraction is close to 78%. And this, for those of you who guessed that this is a reservoir oil, congratulations, that was the correct answer. I know many people, including myself, most likely would have guessed that it would, at least years ago, would guess that this would be a reservoir gas when I saw this distribution, and then changed my mind when I got to this slide right here. And we'll learn much more about compositions and petroleum fluids as we go later. But the importance of this this exercise is to communicate the importance of C7 plus on reservoir fluid classification. Some people say that C7 plus is the soul of PVT. If you really like to understand PVT, you need to understand how much goes into C7 plus, what is the distribution of those components, etc., because that's very sensitive to, for instance, the saturation pressures of near critical fluids, dew points, and these sort of things. So that's the second learning, is related to a very key thing to understand is that heptanes plus, so C7 plus, and how you characterize that if you do reservoir fluid characterization, and if you would like to understand compositional measurements, etc. A lot of the information you can find in C7 plus, or just looking at that particular number and the associated distribution of those components. And on that note, I just wanted to go through the reservoir fluid classifications, now including all the different reservoir fluid types, very, I guess, quickly right here, and also just point out a few rule of thumb numbers in terms of C7 plus, and also the GOR that you can use on a rule of thumb basis when you look at, for instance, compositional measurements, where you might have a C7 plus and maybe a GOR, and you can at least roughly in the landscape of fluids place that particular reservoir fluid in the black oil basket or gas condensate basket, etc. So the most basic reservoir fluid type is the black oil case, where your C7 plus on a rule of thumb basis. So that's important for me to emphasize, that these numbers are a rule of thumb, and they are not, or should not be interpreted as absolute numbers at all. And there will be some overlap between these different ranges, but these, I think, is is okay starting points. So black oil, then you have typically more than 25% C7 plus and less than 1,000 scuffs per barrel GOR. For a volatile oil, you have between 14 to 25 mole percent C7 7 plus, and your GOR would typically be between 1,000 and 3,000. Once you get into the near critical range, that's when your conditions are very close to the so-called critical point. The critical point is where the properties of oil, liquid, and gas converge, so that there's it's essentially not possible to distinguish whether or not this is a gas or a liquid. And for those fluid systems, you would typically have a C7 plus composition of between 11 to 14 and a GOR between 3,000 to 4,000 scuffs per barrel. A very large range is what you would find for gas condensate, because you can have very near critical gas condensates to maybe lean gas condensates, and that's typically between 1 to 11 C7 plus mole percent, and the GORs can be from 4,000 to 100,000. And it's essentially, you know, a gas condensate, the definition of that is that you simply, at the reservoir conditions, needs to have a saturation pressure. And that's a very large compositional range that can essentially yield that. What's important for me to emphasize on this near critical call it fluid type right here is that you can have both. There you can have both bubble points or dew points. So the reservoir, the reservoir fluid type is a little bit arbitrary, but it's either to the right or to the left of the critical point, very close to the critical point. And when you analyze shrinkage curve from, for instance, that type of fluid, you would get a very steep shrinkage. Once you get into the gas space, you have two different types of gas cases that we've looked at already. It's the so-called wet gas, which means that in the reservoir it's always single phase gas, but the surface facilities is inside a two-phase envelope, which you can typically have if you have C7 plus mole percent composition less than 1, and maybe a GOR can be typically more than 100,000. Or if you have a dry gas, then you have essentially 0% C7 plus, and your GOR will be by definition infinite, because you will not have anything in the denominator. I guess what's important for me to emphasize here is that, and we see that from this overview, is that C7 plus represents, or is a good number that represents the components that translates into stock tank sellable fluids at surface. It could also be, we could also have used C6 plus here or C5, but we use C7 plus because it's a very good proxy to communicate fluid type, and also though that part of your fluid that translates into what has the most value, at least per today, which is liquids. If we plot this up on a chart, and we have a GOR on the y-axis and C7 plus mole percent on the x-axis, we can look at where we call it different types of fluids lie. Here we have a very high GOR gas that can be categorized almost as a dry gas. We have a wet gas in this neighborhood. Gas condensate maybe between these branches right here. Near critical fluids in this region, we have an overlap of bubble points and dew points, and there will be also some overlap between these different definitions. So again, just remember that those ranges that we had on the last slides are rules of thumb and are not absolutes, but they're good starting points and good rules of thumb in general. So near critical fluids will contain both bubble points and dew points, and where they are very close to the critical point. The yeah, this range would be the volatile oil range, while this range right here is what we refer to as black oil. So hopefully for many of you, this is a different way of looking at call it classification by using C7 plus mole percent, which is very, very nice thing to be introduced to early, especially if you're working with compositional data, because there's so much information in this. And for instance, when we do studies, one of the things we spend the most time on is actually to study this distribution of components that are equal to or heavier than C7, and we call that heptanes plus characterization or C7 plus characterization, which is very, very important. Yet again, one thing that you probably noticed is the GOR on the y-axis had a star to it. Why did we have a star here? Well, the star refers to that all the GORs here that we see on this plot was processed through the same surface process. So the reason we did that, or Knut Uleberg at Equinor did that, is that if you process all compositions through the same surface process, you're comparing apples to apples. Because as we'll learn and we'll see many times when we create black oil tables, when we talk about in-place volumes, when we talk about formation volume factors, GORs, they are process dependent, or we say that PVT is path dependent. So it depends on how many separator stages you were exposed to at surface, what type of facilities you were exposed to at surface, the conditions of those different call it facility units, etc. So that's very important for me to note here, and you'll hear it many times throughout the course as well, and that's why we have again this message that 1 meter cube is not always to 1 meter cube. So if we have a meter cube from the same well, it can be the exact same reservoir fluid that we produce in terms of composition, but we expose it to 2 different surface processes. We might expose it to a simple 2-stage process, or we expose it to a very, very complex and expensive surface facility network. The amounts that we'll get out from both of those processes in terms of liquid yield and how much liquid versus gas we'll get will be different. And that's what we'll try to just explain here, and which is linked to the course summary, but it's a super important thing to remember when we talk about PVT properties, is that all PVT properties that are volumetrics, so volume factors and GORs, are a function of the surface process that you expose it to, or the path that you expose it to. And many times we call that the compositional path, and that you're path dependent, such that the and it's summarized here in this bullet point that phase split volumes depend on pressure and temperature conditions and the path to get there. So GORs and formation volume factors, which is with BO is an example of that, are process dependent. So we take this animation right here, and if we produced it through this very, very sophisticated surface process right here, we got a surface oil and a surface gas at stock tank conditions. That would be very different than if we exposed it just to a single stage that we produce those fluids straight to stock tank conditions without any processing. And what will happen is that the GOR in this case would be high. The formation volume factor would be higher, which means that your shrinkage is less. Shrinkage factor is less. While here you will have a lower formation volume factor and a lower GOR. And the reason why that is good is that that means that the amount of barrels that you produce at surface for the same reservoir fluid is more. So this is more optimized, if you like. But at the same time, it's also important. Okay, what could we because in both of these cases, the where we measure the GOR, information volume factor, and whatnot, is at stock tank conditions. So at least the conditions here are the same. It's just the path to get to those conditions that are radically different and will yield very, very different results. But you also have to remember what conditions do we measure these GORs at, if you like. So in this case, we actually measure the GOR at the test separated conditions, which in this case is 870 psi and 170 F. So that's very, very different than these stock tank conditions, and you should not in any case, even though it's the same total composition that you produce from the well, compare this these GOR values with the GOR values that you get here. And just to look at this particular example, if you have a total processed well stream through to stock tank conditions, if it's highly sophisticated, you can in this case get, so this is based on some real data, around 840 scuffs per barrel. If you did a single stage flash, you would get 9,250 scuffs per barrel. So per barrel that you produce, you get much more gas, which is of course not good for economics. While the last one is the test separator, which will have a much lower GOR, but here again it comes into play the importance of providing where was this barrel measured. And this barrel was measured at separator conditions, and it's not measured at stock tank conditions. And from this condition down to stock tank, you would have something called your separator oil shrinkage, and gas will come out of solution. And this GOR would most likely, or probably 100% true, be a number between these two numbers right here once we process that to surface. So just remember, when we're talking about GORs, when we're talking about stock tank barrels, when we're talking about separator barrels and reservoir barrels, provide a context. Remember that compositions and PVT is a path-dependent exercise, and you should almost have it in your blood that when you hear a information volume factor number, you should know, first of all, that that's associated with a process. First of all, what is that process? Is that process consistent with the process in reality? And these sort of things. So when we talk about at least PVT internally, we talk about PVT properties, especially black oil PVT properties, we always we actually group them together with the surface process because they are dependent on each other, and when one thing changes, the other thing changes, and that's very important to note. So at this point, this was probably a lot of information, especially if you haven't been exposed to a lot of this before. But this is the course summary kind of thing. So you can also revisit this lesson at the end of the course, such that you can see if we've some of these things might have been come clearer. And if there's still things that are not clear here, feel free to send me an email, and we can get to the bottom of that. Excellent. Good luck with the rest of the course.